Hi, everyone. So we've been doing some testings here with Luis Felipe López during our in-person course, and we want to explain you what we have been doing in a sort of like do it by yourself at home compression test and shear, right? So to start, can you explain, Luis, a little bit about what's compression, what's shear, and why it's so important to understand that to see how strong is the bamboo?
Yes, Luis. So, hello everyone. As Luis was mentioned, right now in the 11 days course here in Bamboo U, we did some homemade tests to at least have a close idea of how strong the bamboo is. And for that purpose, we are using a gadget that we are going to introduce you later that was created by the University of Pittsburgh in the US and INBAR, the International Organization for Bamboo and Rattan. And actually, you can download the plans and the specifications of this gadget so you can do it in your area. So now let's talk about the stresses. Here we have two bamboos, different species. This is a Dendrocalamus asper,
Yep.
and this is a Gigantocloapus. Local name is Petung for this one and Tali for this one. And we have, you see, different specifications for the test. We have an specimen without node and another with node. So to do the test, there is an ISO standard that we use in the laboratory, but you can use it also here to define your specimens. So that standard is the ISO 12257, and it's the standard for laboratory test. Basically, that standard defines the dimensions of the specimen, and it says that the length of the specimen should be close to the diameter of the specimen, but never double the height. So you can play with that height. Here we have 10 centimeters high, and the diameter is 8 centimeters, and here is 10-10. So this is 1-to-1. So with the homemade machine, we can replicate two tests. One is compression, where we are going to crush this bamboo and find the resistance. And the other one is shear, that we are going to create 4 planes of cuttings with using a special bow tie plate, and then we are going to induce the shear parallel. So why these properties are important? There is 8 mechanical properties in bamboo, but 3 of them are the main mechanical properties. So if you want to design with bamboo, you need to know those 3. Those are compression, shear parallel, and bending. For bending, you need to do a full scale test using a full beam that you will see in another video.
Mm-hmm. So basically, people know that bamboo is super strong, and there's people saying that in terms of compression is as strong as concrete, meaning that the compression test that we're doing is like having that vertical force, and that's even stronger or as strong as concrete. How accurate is that idea?
It's super accurate. Actually, a bamboo, like any of these we have on the table, can resist a compression, I will talk in megapascals, from 22 megapascals to 60 megapascals. So that's the range of resistance. Mm-hmm. In engineering, we use lower value because we want to guarantee that the things work well. So let's say the design value for Dendrocalamus asper is 20 megapascals.
20 megapascals.
And that's the resistance of the concrete we use normally in construction.
Yeah.
20 megapascals or 3000 psi. Mm-hmm. So in other words, yes, it's correct. The resistance in compression of bamboo is equal to concrete, but with a difference: weight. Mm-hmm. Yeah. The weight of a cubic meter of bamboo is only 600 kilos, while a cubic meter of concrete has a weight of 2.5 tons. So the difference is 4 times.
Yeah.
So it's incredible heavy, the concrete. So this is a more efficient material in terms of weight and resistance. Plus, we have carbon embedded here, and the concrete actually produces carbon to the atmosphere. So
basically what we're going to do is we want to break and crack this bamboo adding weight. We're gonna calculate that based on megapascals. We did some testings also yesterday to see, for example, how much weight just a square centimeter can hold. So that's one test that we're gonna do. And the other one is shear, which is like, imagine that you have this cylinder of bamboo. Imagine that you have a deck of cards and you just slide that. Because shear, and Luis was mentioning that, shear is also an important property for the bamboo, but it's an interesting one to know about bamboo, which is the weakest.
Yeah, actually, it's compared with the wood, for example, I would say it's like a lower resistance wood in shear, but the disadvantage is that for resisted shear, we only have the thickness that is very small. And what shear produces a crack, actually. And then bamboo, because bamboo only have fibers along its culm, so it's more susceptible to cracks. So those two things combined, the small wall thickness or material to resist the shear, plus the direction of the fibers, create a more easy failure in crack. Mm-hmm. And that you see more often in connections.
Yeah.
So other important aspect to have in comparison compression and shear is that you have an element that is subject to compression and you reach the limit of load, you will have a ductile failure. What does it mean? It means that you will see a deformation that will last for a long period of time before you see a damage. And then, in other words, the structure or the element will tell you,
exactly,
I'm failing.
And that's an important thing if we compare concrete columns and bamboo columns, because that's that thing that is happening with the bamboo when applying a lot of compression and a lot of weight will tell you, so you are able to run out and go out
or fix
that's
but yeah, that's correct, and it works for compression, also for bending. But in terms of shear, again, we don't have that property. Shear is brittle, and then if
explosive.
It's explosive, don't give time, and we don't want that in our construction. So now the challenge for research is produce connections that are more ductile and then avoid the brittle failures. So that's the challenges, but you need to understand well the shear properties of the bamboo because of that.
Okay, so let's crack some bamboo. Let's say that we have some samples. You were mentioning 10 centimeters diameter, 8 and 10 centimeters diameter. So once you have like all these pieces, what's next? How you start measuring wall thickness, height?
So let's take this Dendrocalamus asper. So the first thing you need to define is you use a marker like this one, and then you mark the areas where you are going to take dimensions. So you take the 4 quadrants of the bamboo and both sides. I put a point, so only here and here to have a reference point, so I cannot lose the reference point. And in the homemade test, I will going to use a tape, but if you can use a caliper, it's much better. The caliper will give you more precise dimensions. So first I start taking the dimensions of the diameter. In this case, I will measure 4 diameters, so 2 per each side. So in this case, we have a bamboo, and this first diameter is 104 millimeters. We use millimeters for this purpose. And then I have here 109 millimeters. And in the other direction, I have here 105 millimeters. And in this other direction, I have 103 millimeters. So with that, we already can calculate the average diameter of this specimen. And the second part that we're going to do is to measure the wall thickness. And for the wall thickness, we have to measure in each of these quadrants. So we have to take 8 measurements. So, and you will see that all of them are different. So we have, for example, here, we have 9 millimeters, 10 millimeters, 8 millimeters, 10 millimeters, 8 millimeters, 9 millimeters, 10, and 8 millimeters. So
Could be between 8 and 10 millimeters.
yeah, so an
around
average
10
of
fibers.
9, but of course you need to take note of all these dimensions and make your computation of the average. That's for compression, I only need those two dimensions, diameter and wall thickness. And the area that I am going to use for my calculations is the area of the cylinder. So all this area here. That's the material that can resist the load. So how I calculate the area of this bamboo? Just by using the formula, the geometrical formula for a cylinder. Basically, it's P divided by 4 multiplied by the external diameter square minus the external diameter minus 2 times the wall thickness square. But that's the conventional. So with that, I can define the area of this cylinder. And what we are going to do next is to put the specimen in the machine, test it until we break it, and then you will have a load. Normally, this load is in newtons or in kilograms, and a load itself will don't tell you how strong a material is. Of course, bigger the bamboo, more load you can resist. But the interesting measurement is how much material I have to resist that load. And that will give me exactly how strong the material is. Because I can have, for example, this piece. Normally bamboos are a little bit more strong at the top of the culm than at the bottom. But the bottom resists more load because they are bigger. But when you compare the load with the area, you will see that the top part of the bamboo can resist more kilos per square centimeter. That's
interesting. Why is that happening? Because of the density of the fibers?
So the fibers are continuous from the bottom to the top, but the bamboo is taper. So in the top part of the bamboo, you have a more big concentration of fibers. The density of the bamboo is higher at the top of the culm. And then when you test it, you get higher resistance per square centimeter. So in the single culm. Now, people will say, oh, and now how I will use that in design, for example? But in design, we use the lower value. So we test all the parts of the bamboo, but we use the lower so we can cover the entire culm.
Understood. Okay, let's try to break some
bamboo. Before, let me explain shear. So for shear, guys, we are going to measure exactly the same things. The wall thickness, but the diameter here is important for reference, but the most important is to measure the length of the pole in the 4 areas where I am measuring wall thickness at both sides. Why? Because this is the area, the multiplication of the wall thickness by this length is the area that's going to resist the shear. So in this case, let's see, here for this tally bamboo, we have wall thickness that are an average of 8 millimeters here, 7 millimeters, 7 again, and 7. And then the other side looks even smaller. No, 7 also, 8. This is 7. And then the length, we have 100, 106, 105, 102, and 104. So those are the dimensions we need to take for the shear. Then now let's try to break this, the shear.
Yeah.
Okay.
So with this tool, with this machine, it's the one that we have been using to crack some bamboo here during the course, and that's what we're gonna try to do But first of all, let's explain a little bit of how it works, what's this tool, how the plates are built, and what we're gonna do with that.
Yeah, so Luis, here we have a gadget that was designed by the Pittsburgh University and the INBAR, the International Organization for Bamboo and Rattan. And the basic idea is that you can test specimens in shear or in compression, and then determine the strength of your bamboo. Now, the components it's a very simple gadget that can be fabricated anywhere in the world. You have a bottom plate, a base plate that's strong, steel. You have this jack. You need a gauge that can measure pressure. So that's how we are going to convert the pressure into load. And then we have the plates. And in this case, we have the plates for shear that has this bow tie configuration. Both the plate in the machine here and this plate. And the idea is to allocate the bamboo and the bow tie, and they are placed in opposite directions, so you create the lines of failure here in the border of the tie. So let's place the specimen and proceed with the test. We already took the dimensions of this, so we center the specimen, and the second is to allocate the bow tie in the opposite direction of the. And then once we place the plate, the next step is to align the.
Just level the plates.
Level the plates.
But basically, we're gonna try to crush that bamboo with those two plates.
And then secure the plate at the top. Okay. Right, everything ready. So the ideal test should last more than 2 minutes. So if you get a failure in less than 2 minutes, you are basically pushing the material too quickly. And then bamboo and wood has the ability of the property to resist more in short duration loads. It's like they became more rigid if you apply to the load too fast. So we're trying to do this in a period of time. So you need to be very slowly. Here we are ready to start our test. Luis is my assistant. We will be ready. Careful with the eyes.
Careful, yeah.
Actually, nothing to be worried. This is very safe. No explosions or things is going to happen, but we are going to break the bamboo in shear.
Don't make it at home.
Yeah.
I'm just kidding.
Yeah, actually, the idea is you make it at home. So you can replicate this. Remember, you can find the plans and the specifications of this gadget in the INBAR document for homemade tests. So now we are going to start applying a little bit of pressure to the specimen. And then here we need to be slowly because we don't want to break the bamboo too quickly.
So what is happening now, like you can barely see, but the plate, the bottom plate is getting higher and the bamboo is in between these two plates. What's the pressure now?
Now we have 120 kilograms square centimeter.
100 kilograms, meaning that each centimeter can hold 100 kilograms. Okay. Yes.
Okay, there we go. Okay, now we had break the bamboo, so we can remove the pressure in the jack. And then it can take the specimen. We have the crack here, you can see it. Basically, this is the shear failure. This is what happened when we have a shear failure. It's a slice of bamboo that get out of the rest of the culm. And this is, as I mentioned before, you need to be careful with this kind of failures because they are brittle. Now, we get a maximum of 160 kilograms per square centimeter pressure in the gauge, and now we have to convert that to megapascals or load.
Okay, so we just crack this bamboo and we want to know how much weight, what's the load, and what's the data that we can extract from this test?
Yeah. So after the completion of the test, Luis, so this, you can see the break bamboo, and that we have two planes or two phases of shear failure, but in reality the bamboo was resisting the shear with 4. So you need to use the 4. And then once we have a total pressure in the jack of 160 kilograms per square centimeters, but that pressure we now need to convert in kilograms or newtons. That's what we use to calculate the stress here. So there is a factor that is in the manual I described. In this case is 190, and with that factor we can convert now the pressure of the jack to the force, and the final force resisted by this bamboo was 1.7 tons or 1,770 kilograms. Almost 2 cars, basically, one on top of the other, or 3 elephants. You want to compare with elephants. So, but again, as I explained before, the load itself is not enough. Now we need to divide that load for the 4 areas of these surfaces, and using the average dimensions that we took before for these specimens, we got a total strength of 5.4 megapascals or 54 kilograms per square centimeter.
So meaning that the average that we got, it was the height, it was the thickness of the wall, so then we can calculate that load, and 54 kg, that's the final number. So that's what you want to understand, like how strong it is, but also like the weakness on this shear. And I have a question, like we were applying that shear and that pressure, and we can actually see here where the plates are actually crushing.
Yeah.
And it's very interesting that and also we have another mark here and another mark here, but the shear or the crack is not there.
Yeah.
How
sometimes it happens right in the location of the plates, but in other cases like this one, the failure can be triggered in the thinnest part of the bamboo when they resist less.
Okay.
That creates the cracks. This is the case in the laboratory with more precise equipment, and we are going to see, guys, the test in the laboratory. You can allocate the elements in the right position because we have more precise documents. But even in the laboratory, sometimes this happens also.
Very nice. So this is how strong can be the bamboo. This is how we have been doing the testings here during the in-person course, but also Luis Felipe have been doing a lot of testings. We're going to share also a lot of videos, like with more technical things and technical data. So thank you very much, Luis.
You're welcome, and I hope to you join us in the next videos.